Hello and welcome to Data Science in Industry vlog. In the last video, we was talking about typical steps in a data science project, in a project where we try to implement AI algorithms in the industry sector. Today, I would like to present you the example of a real-life project. I would like to talk about how we optimized district heating network operation in Warsaw, Poland. And it would be a good example of how those steps that were mentioned in the last video are applied in reality. This is a quite big project. We have a forecasting module, optimization module, predictive models, imputation of missing data. So all those topics are covered in one project. That is why I choose this project as the first use case that I would like to show to you. So let's check the agenda of today's video. So first I would like to present you the project goal, present you the district heating network operation. This is necessary to understand the project. Then I would like to talk about the optimizer of a district heating network. First, about the optimizer of a water, of a temperature and pressure of supply water, and the optimizer of pumps. Then I will mention about the optimizer that schedules the operation of CHP plant. And on the end, I would like to present you the algorithm that predicts the heat demand and the algorithm that computes or estimates missing values of crucial parameters that are needed for the algorithm. Okay, so let's start from the basics. I would like to present you the operation of a district heating network, especially the district heating network that is here in Warsaw. So the Warsaw District Heating Network consists of 4 CHP plants. 2 CHP plants are operating on a daily basis every day, and 2 heat sources are, let's say, peak heat sources that are started when there is really cold outside. Then we have around 1,700 kilometers of pipes underground. We have 3 pumping stations and around 16,000 consumers, 16,000 buildings that are connected to the district heating network. So let's try to understand the operation of a district heating network. We have a CHP heat sources, plants where we heat up the water to the desired temperature. In summer it is lower temperature, like for example around, let's say, 60 or 70 centigrades. In the winter time it could be higher, even up to 120 centigrades. Then this hot water from heat sources, those heat sources are generally heat plants that produce only heat, or CHP plants, combined heat and electricity production, right? This is the CHP plant where we produce not only heat but also electricity. So the hot water from the CHP plants go through those pipes. This is called the supply water, and enters the heat exchangers in the building. And there, the heat from the water is transferred to the water that circulates within the building. And this water within the building is used in your radiators, in your rooms, to make you feel comfortable even when it's cold outside. So the heat is transferred to you, to your rooms, via radiators in the rooms. Then the cold water is returning back to the CHP plant. Well, it's not the cold water like, let's say, 5 centigrades. It's still quite hot, but it already the heat. It's the water that is not bringing heat to your homes anymore. It gets back to the plant where it is where the temperature of this water is increased. Also in such exchangers, thanks to the power boilers that are installed, or other sources of energy that are installed in the plants. So the whole operation of this network can be expressed by this equation. I didn't want to put the equation because I know that the number of viewers may drop dramatically if there is an equation in the presentation, but still I will risk and I will present this equation. So the heat transfer is a function of the water flow and the temperature difference, the difference between the temperature of supply water and the temperature of return water, and the heat specific parameter for water. So we can play with the water flow or with the temperature difference in order, if you would like to provide more heat to the users. And in the building there is a controller that controls the flow of the water. So if we want more heat, then the controller will open the valve and more hot water will enter the heat exchanger. So we'll be able to satisfy our heat comfort. So the buildings are deciding about, let's say, about water flow. However, if we increase the supply water temperature in CHP plants, the temperature of the hot water here will be higher, so the flow will drop, will decrease, because the controllers will close the valves. Thus, the district heating network operator has to decide what should be the temperature of the supply water, what should be the temperature of the supply water in each CHP plant to provide enough heat to all users for each moment, for each hour of a day. Of course, we can say that we don't want to heat up the water. We can just try to increase the flow and it's enough. But please remember that pipes have some diameters. Valves cannot open more than 100%. And of course, there must, if we want to have the water flow, there must be a pressure drop in such a heat exchanger in the building, right? So we must push the water to have this flow, and we can do it using pumps. Pumps are located in the plant, in the heat sources, and in some networks, like here in Warsaw, there are dedicated pumping stations that are located in some parts of the city where there is a need for additional pushing, let's say, the water, for additional pressure. Because, for instance, there is we need to pump the water up because of the elevation difference. There we will put such a pumping station. So of course, on the other hand, we can say that we will just increase the temperature, keeping low flow, because we would like to save the cost of pushing the water, of using the pumps. But in this case, we will spend a lot of money on heating up the supply water, and moreover there are some losses in the network. So if the temperature is high, the higher the temperature is, the higher are the losses. So the heat is transferred not only to the buildings but also to the ground, to the air. We don't want to heat up the air in the city. We would like to only transfer heat to the buildings. So the rational approach is to keep as low as possible temperature of supply water and maximize the flow. But in such a case, we have to be sure that we are able to provide the heat to the end user. So we need to be sure that by doing this, we have enough pressure difference, so we really can push the water through the network. We are not exceeding the flow limits in the network, in the chambers, in the substations. Then this solution should be optimal. Okay, so now let's move to the project goal. So Veolia installed in Warsaw a lot of very interesting stuff, like for instance meters that can send the flow, temperature, pressure parameters in a quasi-online time to the data warehouse. We have chambers that can be controlled from the centralized dispatcher center. We can say that this is an intelligent district heating network with a lot of interesting measurements that are sent directly to the data warehouse. And this is a great place for data scientists. If you have a lot of interesting data, we can do something with this. So let's check what was the goal of the part of the system that is called decision support module. And this decision support module is here to help dispatchers run the network. So the decision support module tells the dispatchers what should be the temperature of the supply water for each particular plant, heat source, now, for the next hour, and for the next, in general, 48 or 120 hours. The same with the pressure. What should be the pressure in the heat sources to be able to provide the heat to the user for now and for the next 120 hours. Moreover, the algorithm decides which plant should operate, especially which peak load heat source should be started and when. Maybe today at 7 p.m. we should start this heat source, or maybe during this night we don't need to use the peak load heat source, so that the optimizer tries to recommend what to do in order to deliver the heat that is needed to end user, but to do it with the lowest possible cost at lowest possible impact on the environment. And moreover, we need to also decide how to use those pumping stations for now and for next hours. So what should be the differential pressure associated with those pumping stations on the supply side and on the return side. So the optimal values of these parameters are chosen in a way that allow us to say that the heat will be delivered to end users. And as I say, there are 16,000 end users, and we don't have to look on all of them during the, let's say, detective mode phase of the project. We together with the district heating network operator, we identified critical users, critical substations and chambers. It is assumed that if the heat is delivered to critical customers and chambers, then the heat will be delivered to all the substations and chambers in the network. So we don't have to look on all the 16,000 nodes of this graph. And of course, our decisions have to be in compliance with, have to follow all the technical restrictions. There are some startups stopping times. There is a rate at which the maximum rate of increasing the temperature, etc., etc. Some limits for flow, some limits for pressure, etc., etc. We also have to fulfill all the operational conditions that are defined by dispatchers, and of course all the agreements, the law agreements has to be met. So agreements between the CHP plant and district heating network operator, and between the district heating network operator and end users. I will cover those topics. And of course the physics has to be met. So we cannot violate physics. Those recommendations that we bring must be in line with the thermodynamics. So we started with creating two things, two modules, the forecasting model and the basic optimizer, which is the optimizer that tells us what should be the temperature of supply water, what should be the pressure of supply water, and how to use pumps for the given configuration of operating CHP plants. This is, let's say, the helicopter view of the network, district heating network here in Warsaw. We have 4 heat sources. One is here. This is a base load, the base heat source, which operates always. Another one is here. This is the biggest CHP plant in the EU. It always operates, and there are 2 heat sources, peak load heat sources, that are started when there is really cold outside. So we have to decide, should we start and when to start this or this CHP plant. And the basic optimizer solves the task for a given configuration of operating heat sources. For instance, this, and this. What should be the temperatures, pressures, and operation of pumping stations within the plant. As I told you before, the optimization is the art of decomposition, so we cannot solve everything in one task. It would be too complicated. That is why we split it into 3, but I will present to you here only 2 tasks. One is the task of selecting the sources of heat, and the second task is to solve find the best temperatures and pressures for a given set of CHP plants. Okay, so every time we discussing the optimization task, we need to know the goals. We need to know what are the decision variables, what are the constraints as well. We should only focus on the things that links the decision variables with the goals, decision variables with the constraints. This is how we should work, and this is the outcome of this first step of the data science project, where we have all those workshops with the customers, where we are a detective and we try to summarize the important things and the relations between those things. So the goal is to minimize the network operating cost for the next 48 or 120 hours. What are the costs? The cost of the CHP operation and the cost of the pumping station's operation. And it can be achieved mainly by the minimization of the network heat losses. And as you remember, those heat losses are related with the temperature of the water that circulates within the network. The lower, the better, the lower losses. However, the higher flow. What are the decision variables? As I already told, we can change the supply temperature, we can change the supply pressure, and we can play with the differential pressure in pumping stations. There is a big screen in the central dispatch center where the dispatchers can see the whole network and can decide how to use the pumping stations and what should be sent to the CHP plants, what kind of the temperatures for the next day, today and the next day, what kind of supply pressures should be sent to the plant. We also have some other input parameters that will be very helpful. First of all, the heat demand forecast. I will tell you about this later, but this is a crucial thing. We need to know what would be the consumption of heat in the next hour, tomorrow, in the night, right? So we need to know it with 1 hour resolution. So that is why we created the forecast, which is the input to the optimization model. The forecast is based on the set of deep neural networks. I will talk about this later. We need to know the forecast of the weather, especially the ambient temperature. We need to know what is the configuration of a network, what are the valves positions in the crucial chambers, because it also defines how the network will respond to our decisions. We need to know the current state of the network, because we will calculate recommendations for the current situation. So we need to know what is the current situation, what is the distribution of temperatures, flows, and pressure in heat sources, in substations, and in chambers. And of course, we need to know the cost of heat and electricity prices. So this is the outcome of this workshop with the customer. So what are the constraints? There are many constraints related with the heat source operation, so the temperatures cannot be too high or too low, the same with the pressure. The change of the pressure and of the temperature cannot be too aggressive. You have to be gentle, right? There are some limits for, there is some window for return temperature, so we have to keep the return temperature on the desired level flow constraints. The flow cannot be too low or too high. The same with load. It cannot be too high or too low for the power, right? We have the schedule of the availability of CHP plants that also need to be considered. We have some constraints related with the pumping stations. Of course, each pump has its own characteristic. We have some constraints for the maximum contracted electrical power, for the pressures, for the pressure change. So for each element of the network, we have to identify constraints. And this is typical for all the optimization algorithm. If we know what are the devices in our system, we have to talk with the customer about the constraints related with those devices. And of course, each customer signs the agreement with the network. So the customer knows what would be the temperature of the supply water for a given ambient temperature. Some variations are possible. And if we want to say that the heat will be delivered to the end user for a given water temperature, we need to check that there is that the pressure difference in the substation is higher than some minimum value, right? So, because otherwise we are risking that there will be no flow through the heat exchanger. Moreover, this flow cannot be too high because, of course, there are some limits related with the flow within the building. So if the flow is in the acceptable ranges, if there is enough pressure difference and the temperature that is provided to the user is within the some minimum and maximum value for this particular temperature, we are sure that the heat is delivered to the building. And the most important set of constraints is the physics. Of course, when we are applying data science methods to the industry, to the factory or to the plant, we need to, and let's say some system, industrial system, we need to be sure that all the physics is fulfilled. We are not doing something against the physics. So how to create a model of a district heating network that will cover all those decision variables, all those constraints, and our goals. On one hand, we can use the simulator of a network. There is such a thermodynamic simulator that can be used. The problem is it's, let's say, very heavy. We couldn't use this simulator because the calculation time of the response of, let's say, temperature, pressure, and flow in critical substations to the response to change in supply water temperature, this calculation time was too high, it was very high. And we are just talking about the single run, the single district heating network response to a single decision change. We need to came up with something really simple, because of course the number of iterations in such a task is usually quite high. So we have to use this model many times before we find the optimal solution. That is why we chosen the machine learning approach. So we take the data from plants, from those critical substations, from pumping stations for the last 3 years, and try to create models that will link all the crucial parameters related with constraints, with decision variables, with our optimization goals. And we did it. We had like 2,000 dynamic submodels. They represent the temperature, pressure, and flow response of a network for changes of our decision variables like supply water temperature, like supply water pressure, and changes of the differential pressure within the pumping stations. It turns out that using just real data, historical data, is not enough, because not everything is measured. This is one thing. And another thing, this is typical for optimization projects in industry. When we finally deploy the optimization algorithm, we will start working in a different process operating points. We'll start working with a different water temperature parameters. We will try to explore the solution space more than it is before applying the optimizer. So one of the problems with the data in this project and in many other projects is that the variation of data is not enough. Some parts of the solution space are not covered by the data. Here, how can this is a very abstract discussion, but for instance, in this particular case, the water temperature in one of the heat sources was changing in the same way, had the same value as or very similar value as the water temperature in another heat source. Let's get back to this map. Right, so here we have one heat source, here we have another heat source. So if there was a cold night, the water temperature in this heat source was increased, and the same was made to the water temperature in this heat source. They had the same values. So if we were trying to find a correlation, to find a model that predicts the temperature, let's say in this part of the network, in the northern part of the city, how it will changes, how it will respond to the changes in the heat sources, we are not able to check that this heat source supplies water to this node, because the water temperature trends are the same. Moreover, the quality of the sensor is probably better here, and that is why the machine learning method linked the temperature in this heat source with the temperature in the substation. So it links the temperature in this substation with this heat source, which from the physical point of view is wrong, because it's obvious that this heat source supplies the water to this node. And that is why, in order to increase the variation in the data, we made some additional identification experiments. You can do it on a real plant, on the real system, on a real network. We have done such experiments in power plants or in underground gas storages. But here we had the simulator. That is why we made some experiments based on the simulator, and those experiments extend the variance, increase the variance of data, and get rid of some linear correlations that existed within the data. And because of those linear correlations, we was not able to find a proper model. So based on the data from reality and from identification experiments, where we, for example, just change the temperature in the one heat source and in another experiment in the other heat source. So we cut those linear correlations. We were able to create 2,000 dynamic models that together they make a model, simplified model of the district heating network. Our model should have a desired form, so because we want to use it as a part of the optimization task, as a the model in fact is a constraint in the optimization task. That is why we don't want to use, I know, nonlinear models like decision trees or other models where we cannot calculate derivatives. We would like to have models from which we can take derivatives, because derivatives shows us the direction where to search the optimal value. In this case, we said that we can have linear or quadratic models, because then we can use the, for instance, sequential quadratic programming method as the optimization algorithm, which is fast and accurate. But of course, the reality is more complicated than just quadratic relations. That is why we split our modeling process into the winter, transition, and summer season. So we have different set of models for summer season, different set of models for winter, and different set of models for transition period. So this is, let's say, the input. So we have partitions where we can use linear or quadratic models. Of course, the very important input to the model is the heat demand and our decision variables, because as you remember, we don't want to build a digital twin that will mimic the operation of the whole network. We need our model only to link the decision variables with constraints and goals. This is the only purpose of the predictive model. We don't create predictive models because we like to build them. We are creating them just to solve the optimization task. So we need to know how the change of the supply temperature in a particular CHP plant will affect the return temperature in this particular CHP plant and the flow, how it will affect the supply temperature in the substations and the flow in the substation, the pressure difference. This is we need to know. This is everything we need to know. So we made such 2,000 empirical models, dynamic models, because of course if we change the temperature in the CHP plant, we'll not see the effect of this change immediately. We will see it after 2-3 hours in the winter time, or 8 hours in the summertime, or maybe after the day during the the 8 hours in the transition period, or within a day in the summertime. It all depends on the water flow. If the water flow is high, we will see the change faster, and the water flow is high during the winter time. So it's all mixed. Another challenge is to identify this dynamic. Okay, here's the example of the model results for a supply temperature in the substation. So as you can see, the predicted value here is let's say green or blue, depending how you define this color, or and the original value is red. So you see the models are quite accurate. If the heat demand will change, or we will change the supply temperature of the water, we know how it will affect the supply temperature in the substation. This is one of the relations that we have to cover in our optimization task. And the machine learning approach is very, very handy in this case. If we would like to do it in the standard way, by taking thermodynamic equations and try to solve this system iteratively, it will take way too much time. So this approach cannot be used. In the separate video, I will tell you about which approach is better, to start from physical equations and then simplify it, or to start from pure machine learning and then try to apply some constraints, some framework that we can be sure that those models follows physics, because it's not sometimes it's not obvious. As the example that I presented to you, right? That the machine learning, pure machine learning approach, tell us that the substation in the northern part of the city was taking water from the CHP plant that was located in the southern part of the city. This is stupid. That is why we had to apply some constraints, some expert knowledge here, so our machine learning algorithms can operate within the safe bubbles. So we know that they will not end up with something stupid. Okay, and on the end of the day, this optimizer consists of around 1,000 decision variables, because you remember that we have to calculate it for each hour of the time horizon, and 20,000 constraints. So constraints from the agreements, from the physics, of course the physics is very important, from the some suggestions of dispatchers, from the agreement with the CHP plant that we have to be gentle with our changes of the supply water temperature. On the end of the day, we have such a task. The quality indicator, so the mathematical formulation of our goals, is a quadratic function. The set of constraints is a set of equations and inequations, but all of them are linear or quadratic. That is why we say that we have a quadratic constraints, and all the decision variables are continuous. So we are not deciding if something has to be started or stopped. We are deciding about the pressures and temperatures, right? That is why we split those two optimization tasks. The one task decides which heat source should operate, and those are discrete decision variables, and another task calculates values for continuous decision variables, which is this task. Okay, so now when we know how to calculate the optimum values of the temperature and pressure trajectory in CHP plants and the pressure trajectories in pumping stations, we can define the algorithm that will select which heat source should operate. Right? And this algorithm takes into account the availability of heat plants, the startup time of a heat plants, the stopping time of a heat plants. We can switch them on and off frequently because we will be kicked out of the project within a day or two. So we must follow those constraints. There are some minimum running time and minimum downtime constraints. And of course, we can use some extra expert knowledge about when it is rational to consider this plant to operate. Like, for example, there are two heat sources that are switched on if it's really cold, so there is no need to consider them during the summertime, right? When the weather is hot, we should not uh, start them. This is one of the constraints that help us to reduce the solution space. I will maybe not go into the details of this algorithm. This is a heuristic, which is similar to the algorithm is a heuristic that is similar to the dynamic programming approach. But I'm afraid it will be too boring if I will start presenting this right now. We will lose the whole picture. Maybe this is a topic for another video. In general, we need to decide, should we start this heat source, peak load heat source during this night, or we will be able to live without this heat source in this night. And if we need to start it, then when? At 6 p.m., at 11 p.m., and when to stop it? At 6 a.m., at 5 a.m., or maybe at 9 a.m. So those are the decisions that must be taken, must be calculated by the optimizer. And generally, this whole optimizer is about delivering enough heat to the users for each particular hour of a day. And so we don't want to give more heat that is needed because we will generate losses and we would like to minimize those losses. We don't want to give lower amount of heat because the users will be angry, who will start calling us, hey, I'm cold. What's wrong with those radiators? So we need to be very precise in delivering heat in each particular hour. And please remember that the whole district heating network, especially the big district heating network, and this one is the biggest in EU, they are characterized by long transport delays, big dynamics of this system. So sometimes we need to wait hours and even days to see what is the impact of our decision on the district heating network parameters. Okay, so now let's switch the context, and now let's talk about the heat demand forecast module. So we had two teams. One team was working on the optimizer, and the second team was working on the heat demand forecast, because this is a crucial input to the optimizer. If we have to be very precise in delivering heat, we need to know what is the demand for heat. We have to predict it, and this prediction should be very accurate. So our goal was to create the heat demand for the whole network, for 54 areas and for all the individual substations. And the prediction the forecast horizon was 5 days with hourly resolution. Okay, so we end up with a set of deep neural networks that take into consideration weather data, like wind direction, radiation, temperature, wind speed, humidity, cloudiness, some transformation of this data, like the wind chill parameter, which has such a crazy formula, but this is how we feel we as users. This is how we feel the temperature, and some other transformation. The variables connected with time, so the hour, week of the day, is it a working day or the weekend, information about the holidays, about the Christmas, etc., etc. And of course, if we know the current value of the heat demand, probably the heat demand in the next hour will be similar. That is why we also should use previous outputs as the input to our network. So we can have an autoregressive approach. Oh yeah, but you see that after a while, if we will be basing on the previous output, we will only integrate the error. We will only make the error bigger. So there is a time where we should switch to the model that is not using the previous output. That is why I tell you that this is the combination of a neural network. One is autoregressive neural network, and then we have to automatically switch to the neural network that is not using the previous output. Of course, like in every project, there are a lot of data validation, data cleaning. Actually, there is a module that validates the data in a real time. Here, we had a case where the historical heat demand was measured to some moment of time. And then we didn't have this historical heat demand. So in the time when we start the forecast, we don't have, let's say, the heat demand from the previous hours. We have the heat demand from the, I don't know, 6 hours back. So that is why we could use the historical heat demand to calculate. So that is why, in fact, this forecast starts when there is the last value of the historical heat demand recorded. And we have to simulate what was the historical heat demand up till now and what would be in the future, right? But up till now, we had the historical weather measurements. We didn't have to use the forecast because we know what was the weather. So for the last hour and 2 hours back, we could use the, let's say, the historical weather measurements. But then when we switch to the future, where we are predicting the heat demand in the future, we have to switch to the weather forecast. And this is also typical in the in this type of projects that some parameters are measured, let's say, online, some parameters are not available in the time of when the forecast is executed, and you have to deal with this, right? And then, like I tell you, that for some hour we could use the autoregressive model, but then we know that keeping this autoregressive model to predict the heat consumption in 4 days is useless, because we will want to integrate the error. So we automatically switched, the algorithm automatically switched to just a regressive model without this autoregressive part. So without using the previous outputs. So this is the mixture of, this is not a one model, this is a mixture of models. It's always good to calculate, if you will do such models, it's always good to calculate some confidence intervals, so the end user can see if he can trust, or how much can he trust your forecast, and he can decide if he wants to be aggressive or he wants to be conservative. The dispatcher might want to be conservative and have a big safety margin and use the worst worst scenario of heat demand. Why not? In fact, in our decision support module, we are proposing three different scenarios. Let's say the most probable scenario, let's say the aggressive one, if we really push the network to the limit, and conservative one, the safe one, with a big safety margin. So in case of some failures, breakdowns, we'll be able to deliver heat to end users. There must be some graphical user interface when we can present this demand, and we can present our decisions and the proof that those decisions will work. So basically we are presenting all the parameters of the network in the simulated future. In this particular project, we also automatically execute the simulator. So we send our solution to simulator just to be sure that we are on the safe side. So in the black color here, you can see the real heat demand during the winter time. The red color is predicted heat demand. So those forecasts are quite accurate. This particular project was also a topic for a free PhD thesis. One of the PhD students is now a full PhD, so congratulations for Teresa. We had this program in our team in Translation Technology Science, the program called Applied PhDs. This is a program in Poland that combines industry and the scientific world, so the PhD students can do the real-life projects, and based on those projects, they write their PhD thesis. And if there is a PhD, there must be also a scientific article. So if you would like to read more about the heat demand forecasting in the Warsaw District Heating Network, please read this article published in the Energy Journal last year. And if you would like to read about explainable AI applied, so the methods that tries to explain the AI model, the black box, to the user, you can read this article, also published in Energy. It will be available in December 2022, right by Kuba Białek, another PhD student who was involved in this project. Generally, we like to combine science and real-life projects. And I really encourage all the companies to take part in this program called Application PhD, especially companies in Poland, because the employees can do their PhD and the work is done. So this is a win-win situation for everyone. Last but not least, the missing data imputation module. As you saw, we have 20,000 constraints, 1,000 decision variables, a lot of parameters that must be in place in order to calculate the optimal solution. If the one crucial parameter is missing, one of hundreds of thousands parameters is missing, then we have to show the game over message to the user. But we don't want to do this. This algorithm is used every day on a daily basis by the dispatchers in the Warsaw District Heating Network. They are using it to run the network. So we don't want to show them the game over message if one of the parameters is not in place, is missing. That is why we made a set of algorithms that tries to estimate the missing value. Already discussed it in the last video. This is, for example, the water flow through one of the CHPs. We had the situation when this parameter was missing. but thanks to the algorithm that estimates this value based on water flow in other CHP plants, based on temperatures distribution in the network and in other plants pressures, this model was able to estimate, this was of course a nonlinear model, was able to estimate the missing value like this. Okay, and what are the results of the project? So the annual reduction of CO2 emission is 16,650 tons. So the plants produce, thanks to the application of data science methods to this particular network, the district heating network operator, the Veolia, was able to reduce 16,650 tons of CO2 per year. It's a lot. It results in annual savings around 1 million euro. And it's all because we minimize the heat losses. So we was not using coal or gas to heat up the air, but we was really using it to deliver heat to end users. I must say it was a fascinating project, and of course I want to say a big thank you for Veolia, for the district heating network operator, for good cooperation, to my team of data scientists, and to other teams in the Capital Group Transition Technologies, like software developers, project managers. It can be done by one person. It's a task for a team. And I was lucky that I have great team members. Everyone is specialized in a particular aspect of, like in here, this project. One is very good at defining optimization tasks. One is good in thermodynamics. You really understand the physics behind. Another team member is good in machine learning, and good at forecasting. So together we was able to create this system. So once again, thank you, and I hope you enjoyed. I hope you see the example of the real-life project. If you like such a use cases, I can present more project if it's interesting for you. But for now, I would like to say goodbye, thank you, and if you have any questions, if you would like to discuss some issues from this video, please leave a comment. Bye-bye.